In this video, we're going to be solving for x when x is located in the exponent of an equation. After our recent lessons, you're probably going to look at an equation like this right over here and start to think to yourself that you need to use log. And while that's not incorrect, there are going to be a lot of situations where you don't need to use log at all. We're going to use something that I like to call a swopportunity, and you're going to be using the one-to-one property instead. Before we jump back into everything and get to using log and go over some recent lessons, we're going to really warm up with solving for exponents without logarithmic functions, and instead just using swopportunities and the one-to-one property. When you read a question like this, you really need to just ask yourself, 2 to what power is 8? Coincidentally, that's how you read a logarithmic function anyway. Not that we're going to use it, but just to tie it all back in, this right here is b to the y equals x. I know I have x here. These are all just arbitrary placeholders. Now, if we rewrote this in logarithmic form looks like log base b of x, which equals y. If I fill everything in to the proper place, you'll get log base 2 of 8 equals x. And the question I've been telling you guys that you ask yourself when you see a logarithmic expression, the question you ask yourself is 2 to what power is 8? So the base is where you begin. You begin at the base. The base is in the subscript. 2 to what power is 8? Now you know this answer. I hope you do. The answer to this would be 3. However, in order to be really good at using swopportunities and the one-to-one property, and even to be really good at evaluating log without a calculator, we really need to be very good at knowing all of our basic bases raised to a power. We got to know them by heart. You really don't have a choice. So let's review a few of those right now. The first thing I'm going to have you do is, unless you are incredibly confident, I think it would be a good idea if you wrote down what I have. I know I skipped a few. That's on purpose. Like if you pay attention, I don't have 4 to the 0, and I don't have 5 to the first, or 6 or 7 either to the first or to the 0. Same with 8 and 9. Try to just keep you on your toes a little bit, but I think you should write these down. Now, what I'm going to do in a few minutes, once you press pause, copy it, and then you're ready to go, is I'm going to jump all over this paper and we're going to say what the answers are to every single one of these. I'm not going to write any of them down, and then I'm going to ask you what the answers are, and you have to tell me what the answers are. So if you know them by heart, amazing. If you're going to cheat and use a calculator, I guess, but you still need to know these. So your best bet is to hit pause, write this down, then press pause again so it plays, fill in as we go. I'm not going to write them, but you will. And then you'll be able to answer all the questions correctly because you'll have them all written. Well, if you're pressing play now, let's get to it. You must be ready to go. I'll point, but I'm not going to write down the answers, okay? What is 2 to the 9th power? 2 to the 9 is 512. What is 3 to the 4th power? 3 to the 4th power is 81. 4 to the 3rd power is 64. 2 to the 5th power is 32. 2 to the 8th power is 256. 10 to the 2nd power is 100. 5 to the 3rd is 125. 7 to the second power is 49. 6 to the third power is 216. 2 to the second power is 4. 3 to the 0 power is 1. 5 to the 0 power is 1. 9 to the third power is 729. 8 to the second power is 64. 4 to the first power is 4. 2 to the 0 power is 1. 3 to the third power is 27. 4 to the second power is 16. 10 to the 0 power is 1. 2 to the 10th power is 1024. 3 to the 5th power is 243. 3 to the first power is 3. 2 to the 6th power is 64. 5 to the second power is 25. 8 to the third power is 512. 2 to the first power is 2. 2 to the fourth power is 16. 3 to the second power is 9. 6 to the second power is 36. 10 to the first power is 10. 5 to the fourth power is 625. 9 to the second power is 81. 2 to the seventh power is 128. 10 to the third power is 1000. 2 to the third power is 8. 7 to the third power is 343. 2 to the 11th power is 2048. If you didn't write them down and you're super confident, well, I hope you get them all right, because you're going to need to know them. Solve the given equations for x. Now, we're going to do all of these examples without ever using log. What we have here is 2 to the x equals 8, the same example we mentioned before. What you want to do is to always look for a way to rewrite every expression involved in these problems as the most simple base possible to a power. Is there a number 2 to a power that is equivalent to 8? Yes, it's 2 to the third. This is exactly why it's important that we know all of our simple bases to a power. Sometimes I refer to it as a prime to a power. That's not to say that you'll never be able to use a number that isn't prime to a power, but we always shoot for using a prime number first. So if I know 2 to the x equals 2 to the third, what the one-to-one property basically says is that if you have one base on each side of the equal sign, and those bases are equivalent to each other, then you can basically conclude that the exponents have to be equal to each other. And for this problem, that's all there is to it. We're done. For this next example, the left side's pretty good because we already have a prime number raised to a power. The power is a little bit more intense, but that's okay. The 27 on the other side has to be rewritten, and we're going to rewrite that as 3 to the third power. Now on both sides of the equal sign, we have 3 raised to a power. That's perfect for one-to-one property. That means that we can set the exponents equal to each other. It must be true. X squared plus 2x must equal 3. Now we're left with a polynomial equation, specifically a quadratic. Hopefully everyone remembers how to solve a quadratic equation, how to solve a polynomial. We have to set it equal to 0, and then we're going to jump right into factoring. If you need help with factoring, I will attach a link to some factoring practice videos. Maybe take a few minutes and go over factoring. If you choose not to do that, then you can just carry on. you should be able to get x plus 3, x minus 1. When solving this problem, when we have x plus 3 and x minus 1, we're going to set each of them equal to 0 using zero product property. That gives us x equals negative 3 and x equals 1. For the third problem, we have a lot more going on. 5 to the 2x squared times 25 to the 3x plus 1 equals 1 over 125 times 5 to the negative x. Our exponents even have exponents. If we look at all these numbers, what number do they have in common? What is the common base? How can we rewrite 5, 25, 1 over 125 so that they all have the same base? What would that base be? That base would be 5. So I need to replace 25. I'm going to replace 25 with 5 to the second power. That means I have 5 to the second all raised to the 3x plus 1. We went over our properties of exponents. We'll know what to do with that in the next step. What about 1 over 125? 1 over 125. Well, 125 is 5 to the third. So 1 over 125 is 5 to what power? 5 raised to the, it's got to be a negative exponent. Let that sink in for a second. I'm not going to tell you the answer right away. Let's go back to the left side for a second. We had 5 to the second raised to the 3x plus 1. What do we do? When you raise a power to a power, do you know your properties of exponents? And even 5 to a power times another 5 to a power, there's a rule for that. What do you do with those exponents? Let's refresh our memory. X squared times x cubed is x to the fifth. X squared cubed is x to the sixth. Which one of these do we want to use first? I'm going to concentrate on the 5 to the second raised to the 3x plus 1 first. We're going to multiply those exponents. That will give us 6x plus 2. Now, just to save a few steps of writing, 5 to the 2x squared times 5 to the 6x plus 2 is 5 to a power times 5 to a power. That's when you add your exponents. So we're going to write 5 raised to the 2x squared plus 6x plus 2. Now let's go back to the other side. You had some time to think. 1 over 125 is 5 to what power? I gave you a clue. I said it was negative. It's 5 to the negative third. So again, we have 5 to a power times 5 to a power. We're going to add those exponents. 5 to the negative third plus negative x gives us 5 to the negative 3 minus x. Now we find ourselves in that ideal one-to-one property situation. We have a single base raised to a power on both sides of the equal sign. Those bases are equal to each other. I can't reiterate that enough. You only are allowed to have one base to a power on each side, and those bases have to be equivalent in order for you to use the one-to-one property. We could not use it in a previous step when we had all those other 5s to a power. Now we can set 2x squared plus 6x plus 2 equal to negative 3 minus x. This gives us another polynomial equation to solve, just like the last example. And just like the last example, the polynomial equation we're solving is actually a quadratic. When you solve a polynomial equation, you want to get it equal to 0, factor, and solve with the zero product property. To get this equal to 0, I'll need to add 3 to both sides. I'll need to add x to both sides. When I do that, I'll have 2x squared plus 7x plus 5 equals 0. Again, we need to factor. Factoring here is a little bit more challenging because our leading coefficient is not 1. If you didn't look back at the factoring help before, I definitely think you should go and look at it now if you are nervous about factoring. I promise factoring doesn't go away. I'm not going to go over these lessons now. You have the resources. You have to take it upon yourself to refresh your memory. In factored form, we'll have 2x plus 5 times x plus 1. Now, when solving a factored polynomial, we use the zero product property. We set each factor equal to 0. I'm not showing the work. We've done a ton of practice with this. The answers we will get when solving are x equals negative 5 over 2 and x equals negative 1. The domain of exponential equations is all real numbers, so there was nothing to go back and check. Here in this next example, it looks pretty straightforward. We have 6 to a power equals 6 to a power. It's not a trick. You're ready to go. That means the exponent on the left has to equal the exponent on the right. Negative 6x minus x squared equals 8. It's not going away. We have another factoring problem. We want to get this equal to 0. I'm going to bring everything to the right side because I'd rather have my leading term, x squared, positive. So I'll add x squared to both sides, and I'll add 6x to both sides. X squared plus 6x plus 8. Factored, third time. If you didn't look it up before, if you didn't watch, review, or practice, do it now if you're insecure. Factored, we'll have x plus 4, x plus 2. Zero product property, x equals negative 4, x equals negative 2. Again, the domain of exponential functions is all real numbers. We have nothing to check. The examples we did today were solving exponential equations, solving for a variable and an exponent, but the examples that did not require the use of log. Maybe you'll understand a little bit better what it is we're doing when we are solving with log. It seems that too many people get nervous and panic because it looks different, when really I promise you have the reasoning, the skills, and the ability to solve using log properly. But like I said, I wanted to take some time to go over problems where log was not necessary. I hope that this helps you. I hope that this also refreshes your memory on factoring, properties of exponents, different numbers to a power, and we just strengthen all of our fluency skills, our foundational skills, so that moving forward we can do a really great job with this unit.